Hello, everyone. Thank you for joining us today. My name's Matt Hine, and I'll be presenting Scalable 3D Cloud Visualization for Industrial Applications. I'm with Vertex, and I'm also joined by Mike McCarty, who's a principal engineer at Vertex. Our background, I've got 15 plus years of experience in 3D visualization, data science, machine learning, and in particular, an interest in cloud computing applications. I was at the Virtual Reality Application Center at Iowa State about 15 years ago and did a lot of interesting things at the time with high performance computing, along with kind of 3D scientific visualization. I'm joined by Mike McCarty here, who Mike spent a long time at companies such as Engineering Animation, UGS, and Siemens, working on 3D visualization for CAD and PLM data and high performance software. I'm going to start out with talking about what Vertex was trying to solve with our cloud-based visualization. Industry 4.0 is a broad term that generally refers to the fourth industrial revolution, which you can really think about in terms of digitization of manufacturing processes. And so that's, all the way from engineering to the customer, trying to shorten sales cycles, increasing factory yield and defect reporting, things like, being able to have a digital service for field service maintenance, digital twins, supplier collaboration. So there's a lot of interesting problems that Industry 4.0 is meant to tackle through that digitization process. The problem that I often see, and our Vertex customers and users often see, is a lot of these digital processes want to use the 3D CAD data downstream. So, again, think about a salesperson trying to show a customer what they're actually going to build. There's a lot of engineering to order type applications, digital twins for field service, getting 3D on the shop floor in a manufacturing setting. And traditionally, this has been somewhat difficult process. To start off with, you often require expensive hardware to be able to visualize that engineering CAD data. And even if you have that hardware, you often need installed software to be able to do it. And then if you have that installed software, the user interface is often too complex. A lot of 3D CAD applications and the resulting downstream lightweight viewers are often made by taking the original CAD user interface paradigms and kind of stripping them down, and it's still too confusing to those end users. And then often engineering CAD data is the most IP sensitive data within the manufacturing organization, and trying to get that CAD data out into the hands of someone else that can actually use it. There's a lot of just security challenges, and also challenges with just streaming that kind of data to downstream. So it's very large file sizes. So traditionally, what we see in order for you to be able to get your engineering CAD data downstream, you talk about getting the native CAD data, reducing that CAD data down to an exchange format, like a lightweight file. But then you often need to get levels of detail and things like that figured out so that you can get that onto different devices. Some things that are common out there, using game development engines, but also things like WebGL. The problem with we see with WebGL, you just end up with poor quality representations, low fidelity. It's somewhat specific to device in terms of the performance characteristics because WebGL is still using GPU on the device. And the more hoops that you jump through here, the more disconnected you become to that source of truth within engineering. And like I said, with security and IP type issues in mind, you are at the end of the day still streaming these assets to different devices. So one of the things that we set out to do with Vertex is kind of eliminate some of these challenges. So it's hard, expensive, time consuming in order to get assets downstream. So we built Vertex as a 3D cloud platform where we're doing 100% of our rendering server side. So what we do is we'll take that original engineering CAD data, import it into our platform, translate that, and we don't really have a file format. We take that model apart, store it off in a number of different databases, and from there, stream images. And so this isn't something like where I'm just screen scraping some headless application in the cloud. We're actually generating images on the fly with every user interaction with our platform, and taking the resulting camera angles, sending that to our processors, and then having a distributed application algorithm to generate those images and then stream those back to the client. And Mike will talk about that in a couple minutes here. We see this benefit of just streaming images. You get high quality data, and we can dynamically change the resolution anytime we want. You can because this is device independent rendering, you can render on any device, any user, anywhere in the world. And we're connected directly back to that PLM source of truth for that CAD data. We also view this much more secure than traditional asset streaming, because you're just sending pixels back to the device. So I'll give you a demo of this in a second, but our platform, we've really geared this to these industrial applications for Industry 4.0. We have packaged up our platform with a turnkey application, but in the last year or so, we've built out a 3D SDK on the platform that's 100% cloud-based. So there's really no need to have any plugins or installs or anything like that. We can basically stream images to any web device. What makes us different compared to some of the other traditional methods here? Again, like we're 100% cloud-based server-side rendering using only CPUs. So we try to get the lowest cost high-end CPU that we can from cloud providers, not using any of the GPU capabilities there. That really helps us cut down on costs, which is very important to industrial applications, just because the number of potential users out there. So if you think like a field service example, you've got tens of thousands, hundreds of thousands of people wanting to be able to pull up like on this example, an engine, to be able to look at 3D work instructions. Our architecture enables us to have linear scaling, high-speed multi-CAD imports, and at the end of the day, we feel like this is very well suited for 3D applications on mobile and low-powered devices. Just to help understand some of the benchmarking that we've performed, I can't really show this here, but we do have a commercial aircraft model that we use for load testing. We can't show it because it's customer data, and we don't have the ability to permission to show that. But that file size for that model, 1.3 gigabytes. around 140,000 parts, 220 million triangles. Once we import that model initially, it's about 4 minutes to be able to translate that model and import it into the Vertex platform. But once you do that, every subsequent load's instantaneous. And through our load testing, we've tested around 1,500 users, simulated, beefing that up to about 210 parts and 330 billion triangles, and again on a single server-side cluster there. And our benchmarking, we do this for quality and load tests ourselves. We ran that for about 3 hours with randomized camera views and achieved a frame rate of about 15 frames per second. And now let me just give you a taste of the demo here, and then I'll let my colleague Mike talk about our architecture. I'm on the Vertex developer portal, and if you go to developer.vertexviz.com and click on the examples, we've got a number of industrial application examples, which, by the way, are 100% open source here. So I'm going to click 3D work instructions, launch the app. So I pulled up, this is an automotive model here. So again, you can see every time I kind of move the mouse, we're regenerating images. And again, if I were to disable WebGL in this browser, there's no reliance on WebGL at all. This is simply just streaming images over the wire. So we can build applications like this pretty quickly. I could say, begin assembly and kind of show the standard type work instructions demo. The great thing about this is, again, we're using the native engineering CAD data to render this. You're not stepping through a number of different processes to get your data in here, which we commonly run into with our customers. This really helps save time and energy in terms of being able to reuse the CAD data, not just for work instructions, but then you can also think about some of those other downstream use cases like sales and service, and the new things, the digital twin, where I can pull in actual performance data and be able to inject that back into my 3D geometry. Just for some size comparison before I turn it over to Mike here, I've built this factory of the same CAD model, and I'm gonna zoom in here. So again, every time I move my mouse, my cursor here, and change the camera view, I can get new images. And so this is just providing a walkthrough. And again, if I was trying to model this for a factory, I can take the actual model as it exists in the PLM system for that particular station and be able to render that very performantly. With that, I'm going to switch over to Mike so he can kind of talk through how we're doing this. Go ahead, Mike.
Thanks, Matt. Sure. So the first thing I want to talk about is the principles that underlie our rendering architecture. The first thing is, I think the main focus here was unbounded scalability. So that is concurrent number of users and scene complexity. So we believe that there will always be a case for more concurrent users and larger, more complex scenes, and therefore we never assume that there's an upper limit on our scale, and our software is designed accordingly. Massively parallel. Our architecture, our implementation is cloud native and is designed from the ground up to maximize the use of our hardware resources. Low latency, good end user experience demands a highly interactive, highly responsive rendering engine. Highly secure. This is another one of these fundamental tenets. We are SOC 2 compliant, which means that we follow all the security best practices to ensure that the data that our customers entrust with us is always secure when in transit and at rest. 3D design data is often our customers' most valuable and sensitive intellectual property. So once it's in the Vertex environment, that 3D data doesn't leave our cloud environment for rendering, which is what Matt was showing you there. And of course, fault tolerance. You learn very quickly when you're working in a cloud environment that what fault tolerance means and how it can be difficult to achieve. Network outages happen at any time and any place. So every part of our system has mitigation strategies and failover logic. Ultra low cost, which Matt referred to a little bit earlier. CPU versus GPU. GPUs are fast, but they're also expensive. Being as we're CPU based, Vertex is able to be order of magnitude less expensive than comparable GPU-based remote rendering services. And adaptive load management. Our scaling technology maintains a statistical model of the observed load, so it's able to intelligently deploy hardware resources as needed without impacting performance or availability. And we combine these principles in a way that allowed us to be awarded a patent in the US for the design of our core rendering architecture. The patent describes several concepts that work together to make this architecture successful in practice. The first is sharding. So this is a process of subdividing the geometry and the scenes into spatially compact shards. This enhances scalability, IP security, and enables wide-scale parallelism. Spatial culling is a common technique. We deploy several culling techniques, including view frustum culling, screen size culling, occlusion culling, and to enhance scalability and latency performance. And then last but certainly not least, distributed rendering. So this is our ability to use every opportunity to leverage the wide scale parallelism as we're executing each rendering task. This naturally improves fault tolerance as we can seamlessly redistribute work throughout the system when a fault is discovered and it's in recovering from that. So how does this all work in practice? So we start with a client application. This could be a JavaScript web app that's running inside of your browser. This could be an app running natively on your phone or your tablet. That application will establishes an HTTP connection with the Vertex REST APIs to begin a rendering session. So the app is then connected with a streaming service within our cloud environment. The service handles all the rendering client communication and the data streaming with the client application. So, and it does this all securely. Any frame requests from the client application are forwarded to a routing service, which coordinates the high-level load balancing based on a statistical model of user activity. So this is the highest level load balancing technology. And then from there, the work, a VRU is selected from a cluster of VRUs to perform the work. VRU is short for virtual rendering unit and is a logical grouping of hardware and software resources designed to work in a coordinated fashion to execute the rendering task as efficiently as possible. VRUs are at the heart of our scaling solution and are designed to automatically scale in and scale out as user demand dictates. Each VRU pulls scene and geometry data from high-speed databases as it produces images of the requested scene, and then finally the image is passed back through the streaming service, and finally back to the client application for display. In terms of scalability, I just want to show you some actual graphs from a load test that we run periodically internally to validate the behavior of our scaling implementation. So in this particular test, we start from 0 users and gradually ramp up the number of concurrent users. And then each user, once they come on, once that session is established, they begin requesting new frames at a rate of 15 frames per second, and at a resolution of 1920 by 1080. So this is that would be your standard 1080p resolution image. And each user has a replica of the scene, which has approximately 130,000 items in it, for a grand total of around 200 million triangles. So this is a non-trivial scene at the very least. So here you can see that here's the graph of the user sessions increasing over time, and again, each one of these, as each user signs on, they begin requesting frames at 15 frames per second. And then you can also see the observed frame rate. So this is the monitoring of what are these user sessions experiencing in terms of frame rate, in terms of interactivity, and you can see that it reaches a sustained level of 15 frames per second, which means that there is no reduction in perceived performance as new users come on. And then this final graph is the rendering capacity. So what's happening behind the scenes here is the increased workload, but through the addition of new users, triggers our scaling logic to provision additional hardware, increasing our rendering capacity proportionally to meet the need without any drop off in frame rate or latency from the user's perspective. Not shown here, but conversely, as user demand falls back off, as you might expect at the end, say at the end of the workday, number of user sessions will start decreasing. The scaling logic will also reduce capacity in line with the drop in demand. All of this scaling in and out is performed automatically and is 100% transparent to the user. That's all I have. If you have any questions, we'd love to answer them. Thank you.
Yeah, thanks, Mike. So now I think we have time for a few questions. If we don't get to your questions, please visit us at the virtual booth or reach out to Mike and I on LinkedIn or something like that. Thank you very much.